Numbers on the far right represent how many miles away these planets are from the sun. Mercury, 36 million miles. And that's just like an inch in comparison now to the galaxy. Not even like an inch. It's more like just a speck, just a centimeter there. So don't think of 36 million miles being very far. It's just a rock's throw. Venus, 67 million miles. Earth, 93 million. Mars, 142 million. Jupiter, 486 million. Saturn, 892 million. Then we get out to Uranus, 1.8 billion miles. Neptune, 2.8 billion. Pluto, 3.7 billion miles away from the sun. The standard figure to remember is the Earth's figure, and that's known as 1 AU, an astronomical unit. It's 93 million miles. And sometimes you'll see things measured in AUs. Rather than just measuring it in miles, measure it in groups of 93 million miles at a time, and that's one astronomical unit. Now, we'll come back to these probably later on, but these are all included. They're not mentioned here, but obviously they're all included here now on the fourth day of creation. All these other planets are included in being created along with the sun, the moon, and the stars. Now, we've talked about the various moons that some of the planets have beforehand. You know that our planet has one. Most of our moons are found in what we call our Jovian planets. These are our light, gaseous planets that we find out here on the outside. So whenever the Earth has her moon created, then we've got the moons of these other planets along with the planets themselves, the mother planet themselves, being created at this time. But notice the Earth happens to be just at the right point. It's not too hot and it's not too cold away from the sun. It seems like the planet Mercury has a temperature of 800 degrees Fahrenheit on the sunlit side and 200 degrees below zero on the side that's away from the sun. Now, what do you think causes that? We're further away, but we don't have temperatures as cold as 200. What do you think causes that? They don't have an atmosphere. You see, it's your atmosphere that regulates your temperature. You've got to have an atmosphere if you want to have any type of uniform temperature on the planet. So our closest planet here, Mercury, doesn't have an atmosphere. So whenever it faces the sun, it cooks up to 800 degrees. And then whenever it turns away from the sun, it cools down 1,000 degrees and goes to 200 below zero. So obviously you can't live under conditions like that. Venus is not much better. And when you get out to Pluto, it's so cold you wouldn't want to live out that far away from the sun either. So God's done all this for variety's sake, so that the heavens can manifest His glory. And He made this third planet, Earth, right in the particular correct place so it could receive enough heat, warmth from the sun, stay warm when it needed to be warm, and it could also cool off a little bit and not get too hot on us. That's not taking into account some other things that we'll say about the atmosphere. But whether you're pre-flood or post-flood, the Earth is still right in the right place to have a nice atmosphere. Don't ever complain about the 100-degree temperature, because it could be 800 degrees here just as easily if we were a little bit closer. I guess we would have had to have been made a little bit different to be able to stand a temperature like that. Well, just how big do you think all these things are that we're looking at here? So you want to know, someone asked, you want to know how big it is? How big is it? All right, let's talk about how vast the universe really is here. This is, you'll have to listen with all 3 ears, because this is absolutely phenomenal to even begin to comprehend how vast and at the same time how small the universe is. Our galaxy, the Milky Way galaxy, is 100,000 light years in length. And it's 5.5 times longer than it is wide. I've got some comparisons that I'll give you here in a moment to help you understand exactly what that is. Now, whenever we start reaching out into outer space, we stop measuring things in miles because we'd run out of zeros to put after the number to figure out how many miles it is. And eventually we'd run out of zeros even if we measured it in AUs, that is a 93 million mile chunk all at the same time. So scientists have invented another way to measure distance, and that's known as a light year. Now, a light year sounds like a measure of time because you've got time in their year, but a light year is a measure of distance. A light year, obviously, is the distance that light will travel in 1 year. That you have to break down to realize that if it's going 186,000 miles a second, then you find out how many seconds are in a year, and then you can find out how many miles light can travel in 1 year. Now, if our galaxy, our Milky Way, is 100,000 light years long, and this is a measure of distance, then you'd have to find out, first of all, that light travels 186,000 miles a second, then find out how many seconds are in 100,000 years. Multiply the number of seconds by 186,000 MPS, and that would be the distance of miles where light would go in a period of 100,000 years. Now, a year here on this planet is going to, of course, be a lot different than a light year because it travels so fast. Another measurement that broadens it and helps you understand it more is that light travels at 700 million miles per hour. 186,000 miles a second, 700 million miles per hour. One light year equals 6 trillion miles. 1 light year equals 6 trillion miles. Well, see, that's why they stopped counting in miles there, because the light year is, again, just a stone's throw. So when you really start wanting to count up and find out how far away something is, you can't say, now it's 4 city blocks or 18 miles or even 100 trillion million zillion miles. You've got to say it's so many light years away, and that breaks it down for you. Now, let me give you a couple of examples here to explain to you how vast. If you can get these down, fine. If not, that's okay too. But I copied these down somewhere some time ago because they'll help you understand what we're looking at, first of all, on how vast the universe is. Let's assume that the thickness of this piece of paper, not the length or the width or anything, but this thickness, which if this was held perfectly straight and aimed perfectly at your eye, I guess you realize you could hardly see that, it's so thin. Now, you can see it because it's got a tilt to it, but if that was stretched taut and held perfect with your eyes, it's so thin you can probably not see that. Let's assume that the thickness of a piece of notebook paper, this is typing paper, I type my notes, typing paper represents 93 million miles, or 1 AU. All right, that's step one. To represent the distance to the nearest star, we would need a stack of paper 71 feet high. That represents the distance to the nearest star. Not counting our sun now. We call the sun even though it's a star. That means you've got to get outside of our solar system into another part of the galaxy to get close to another star, which is Alpha Centauri, the nearest star. It would take you a stack of paper 71 feet high. In order to get a comparison of the diameter of the Milky Way, you would need a stack of paper 310 miles high. If one of these now was 93 million miles, then to represent the diameter of our galaxy, you'd need a stack of paper 310 miles high. And to get to the edge of the known universe, you would need a stack of paper, listen to this, 31 million miles high. If each paper was 93 million miles, you would need a stack of them that stretched up 31 million miles, and that would take you from us to the edge of our known universe. That's called the paper stack model. Then, secondly, there's the orange sand model. And it goes like this. Let's assume that an orange represents the sun. Then the earth would be a piece of sand circling at 30 feet away. A piece of sand, a speck, a grain of sand compared to the size of an orange would be a comparison of the earth to the sun, and it would be 30 feet away from this orange. Pluto would be another grain of sand. You've got that down. That was on the map. Pluto would be another grain of sand circling the orange at 10 city blocks away. Then the nearest star, if all this is true thus far, the nearest star would be 1,300 miles from the orange. Now you see, when you look up there and you see all those stars, it looks like they're that close together. But they are just millions and millions of miles away from each other, though. But when something gets that far away, of course, it appears to be closer together then. When it gets far away like that, it looks like it's closer together. But you don't have stars that are sitting right side by side each other. They couldn't do that. The gravitational forces wouldn't let stars sit side by side like that. So you're looking at all those stars. When you go outside and look on a clear night, you, with the naked eye, can see on the average of 5,000 stars. And that's what you can see now with your naked eye. And a lot of those appear to be in little clusters all grouped together. But those little clusters, the space separating those stars is just millions and millions of miles apart. Another way to represent how vast this is that 1.3 million Earths would fit into the sun. That's the size of the Earth compared to the sun. 1.3 million of our planet Earth could be placed in the sun if we could scoop it out and hollow it out. And we could put 1.3 million Earths inside. Now I ask an interesting question. Does the universe, or does heaven, have an end somewhere? Now remember the paper stack example that we gave there. The edge of the known universe would take a stack of papers 31 million miles high to represent the known edge of the universe. And it's a long way away. But do you think that's really the end, where they have spotted their latest quasar? Someone spotted a new quasar there. That's the only way you can find these great distances. You can't even see stars when they get that far away. I'm talking about like 12 billion light years away. That's how far the edge of the known galaxy is, 12 billion light years. And the only way you can determine that is if you've got a quasar that's going off somewhere in that area, because then it's powerful enough to generate enough light and energy back here to the Earth that you could see it. But do you think that's the end of it? Does it have an end? Well, we got some yes and some no's. Or to change the question, or to reword it another way, is space infinite, or the opposite, is space finite? Finite or infinite? Finite. You might not fully understand this, but I'll show you how space is finite. Only God is infinite. I'll show you. This is remarkable. You got to really, it's going to go past you so quick you probably won't catch it. There's space right here on the end of this, and I'm going to put this right here. Now this is occupying space. Space used to be here. Now there's a pen sitting here. Now can I put this pointer in the space where this is now? Can't do that. That means space is finite right away. See, there's more space over here. Now I can put this here. Now this is in space over here. Now can I put this in that space where this is? Can't do that. Space is finite there. All of you catch that now? Got to think about that a while. Well, if you think that space is infinite, you think man will ever find an alleged end to it? Well, certainly he's found what he thinks is an alleged end to it. let's just assume that space is finite. That it has, in other words, that it has an end somewhere. Do you think that man will find that? Turn over to Jeremiah 31. The Bible answers that. This goes way beyond what you can really comprehend, where you can think, now, where could there actually be an end to space? Because if you got to the place where there's an end, then couldn't you just stick your arm right through it, and there would be some other space for your arm to occupy on the other side? But don't you realize if you got to the very end of it, it's not going to be a solid wall or anything there. But don't you realize you couldn't stick your hand through it because there's no space on the other side of that then? And you would be to the end. You couldn't run into the end. You couldn't walk through the end. You couldn't see through it. You couldn't stick your hand through it. But that would be the end of space, or the universe. Jeremiah 31:37. Thus saith the Lord, if heaven above can be measured, and the foundations of the earth searched out beneath, then I will also cast off all the seed of Israel for all that they have done, saith the Lord. Well, he's promising the Word he'll never cast Israel off. So that answers the question, can you ever find the end of what is finite heaven? No. Because if you think about this, man's trying to find the end. As soon as he finds the end, Israel is doomed forever. That's what the prophecy says here. If you find the end of heaven, or he said if you can search out the foundations of the earth, you won't be digging down to the center of the earth. Contrary to Jules Verne and everyone else, you'll never get to the center of the earth. And if you do, you can search out the center of the earth. Of course, it just gets hotter and hotter the deeper you get. No telling what's going to be down there in the very middle when you get there. But if you could get down there and search out the foundations of the earth, then the nation of Israel is lost forever. And if you can search out the heavens and find the end of the heavens, or measure the heavens, now God can measure them. There's a scripture over in Isaiah 40. God knows how big heaven is. Only God is infinite. That means space is finite, and that means it comes to an end somewhere. What's beyond that? Nothing is beyond that. There's no space, there's nothing beyond that. But it comes to an end. Isaiah 40 in verse 12. Who hath measured the waters in the hollow of his hand? 71% of the earth, surface, water. God said he can fit in the palm of his hand. And meted out heaven, that is, he measured out heaven with a span. Now a span is the distance of a man's hand where you open it up real broad and set a ruler right on top and draw a line straight down to my thumb and draw a line straight down to my little finger, which on the average is 9 inches. That's how big a span is, 9 inches. You put a ruler right there, draw an imaginary line down to my thumb, and then down to my little finger, you've got 9 inches. So you see what God said? He said the heavens to me are about 9 inches long. And we were just looking at how big it was here. We can't even begin to comprehend it. He said to me, it's about a span long. And comprehended the dust of the earth in a measure, and weighed the mountains in scales, and the hills in a balance. Who hath directed the Spirit, capital S, of the Lord, or being his counselor hath taught him? With whom took he counsel, and whom instructed him, and taught him in the path of judgment, and taught him knowledge, and showed to him the way of understanding? Behold, the nations are as a drop in the bucket. That's where we get that phrase, something just a drop in the bucket. You get that from Isaiah 40:15. All the nations are a drop in the bucket, and are counted as the small dust of the balance. Behold, he taketh up the isles as a very little thing. And Lebanon is not sufficient to burn. Now he's referring to the great cedars of Lebanon. Lebanon was famous for its great cedars. And he said, if I were cold, all the cedars in Lebanon couldn't warm me up. Nor the beasts thereof sufficient for a burnt offering. He said, if I was hungry and you sacrificed all the beasts of the field, he said, I'd still be hungry. All nations before him are as nothing. and they are counted to him less than nothing. I mean, how can you get less than nothing? And he said, all the nations to me are less than nothing in vanity. Well, then, to whom will we liken God, or what likeness will ye compare unto him? You see why you get in some of these areas, you can't explain them? He just said, all right, now tell me who you're going to compare God to. How can you compare him to anything else? And say, now I want to describe some things about God to you. Just the Godhead. How are you going to describe the Godhead to someone? When the Bible says, to whom then will ye liken God? We've got a piece of paper here. We're trying to liken the universe to it, and we're not doing a very good job of that. Still goes beyond your understanding. And if God says the universe is only 9 inches to me, then what are you going to use to compare what God's like? Or what likeness will ye compare unto him? And then people want to criticize us because we don't take medicine. You know, of all things. The workman melteth a graven image. Now he's going to go into idolatry. Men are so floored at how big God is, they're just going to reject him and make themselves an old graven image. The goldsmith spreadeth it over with gold and casteth silver chains, and he that is so impoverished that he hath no oblation chooseth a tree that will not rot. He seeketh unto him a cunning workman to prepare a graven image that shall not be moved. Have ye not known, have ye not heard? Hath it not been told you from the beginning? Have ye not understood from the foundations of the earth? It is he that sitteth on the circle of the earth. The inhabitants thereof are as grasshoppers, that stretcheth out the heavens as a curtain, and spreadeth them out as a tent to dwell in. Verse 28, hast thou not known, hast thou not heard, that the everlasting God, the Lord, the creator of the ends of the earth, fainteth not, neither is weary, and there is no searching of his understanding. The whole chapter in praise of just how great God really is. And we know that heaven has to be finite simply because it's something created. And if it's created, it's got to have an end somewhere to it. It has a beginning and it's got an end somewhere. It has a beginning in time and it's got an end somewhere in space. The mind couldn't really even conceive of something that God created that's infinite in space, that is. How could you create something and make it infinite in space? You just couldn't do that. And that's a contradiction in terms. That's a contradiction right away. To create something that's infinite. Because just by means of creating whatever it is you're creating, then it's got to be finite. That we demonstrated by showing you right here. Another pulpit can't sit where this pulpit is. That means space is finite. It has certain limitations to it. Namely, it can only house one object here at a time. One solid object like this pulpit. We had another pulpit that was made identical to this. It couldn't sit right where this one is sitting because space is finite and it's already occupied by this pulpit that is sitting here. All right, that gives you some idea now of how large space or the universe is. Let's talk for a moment about how small it is. And it's almost as infinitesimally small as it is large. And by small, I mean the components that make up the universe. And for this, we have to go to our simple structure, the atom. Now, everything that's in the universe is made up of the atom. Now, when you get all of them together, you can see just how big of a thing we can really have, and we end up with the universe. But when you go back to the other end of the spectrum and go down small, you can see just how infinitesimally small the universe is, that is, the components of the universe, in comparison to anything else. And I've got several examples to give you here on just how small the atom really is. Now, an atom, of course, has a neutron and proton that make up the nucleus and a shell of electrons that spin around the outside. I assume all of you know that. If you don't, then praise the Lord, you just learned it. It's got a neutron, a proton that make up the nucleus. It's got a shell of electrons, sometimes several shells of electrons that spin around the outside. Now, this is just fascinating when you think about it. As I've shared with you before, that means this pulpit is moving while it's sitting here. And what keeps it from being a gas as opposed to a solid all depends on the rate of spin and the number of those electrons in the outer shell. Now, the inner shell doesn't make a lot of difference. But the outer shell, the shell that's on the outside of the atom, if you have enough electrons and they're spinning fast enough, then you end up with something solid that you can't push your finger through. When you've got a gaseous material, you've still got a nucleus with a proton and a neutron, and you still got shells of electrons that go around the outside, but you don't have that many of them, nor are they going as fast as the ones in a solid material like this. Therefore, you can push your finger right through it. But if you could break this down, you've got nothing but little moving parts that are just running and spinning all over the place. All right? Let me give you some ideas of just how small they really are. I don't have a ballpoint pen. I'll use this. On the tip, that's pretty small. On the tip of a ballpoint pen, there are so many atoms that if an army were to carry these atoms, one atom per man, marching 4 abreast, it would take them 20,000 years to walk by you. I'll say that again. On the tip of a pen, there are so many atoms. Now, we're not even talking about the neutrons or protons in them. We're just talking about the big thing, the big atom. There are so many atoms on the tip of a pen that if an army were to take one atom per man, marching 4 abreast, you'd have your first row of 4 men. Each one of them would be carrying one atom. You'd have a row behind them of 4 men. Each one of them would be carrying one atom. So forth. You'd have these rows of 4 men. It would take them 20,000 years to walk in front of you. You see, that's just to get the atoms off the tip of a pen. $20,000 years to march past you. Another comparison, it would take 25 trillion protons laid side by side to equal 1 linear inch. $25 trillion protons laid side by side to equal a linear inch. Another comparison, there are as many protons in a cubic inch of copper. Now that's a cube now, not a square. There are as many protons in a cubic inch of copper as there are what? Who wants to take a guess? What? Close, get down to the earth. No? What would you compare that to? There are as many protons in a cubic inch of copper. Drops of water in the ocean plus something else. Grains of sand on the seashore. Now, how many grains of sand on the seashore? Be honest, you think there really are. And how many drops of water, if you want to count one drop at a time, drop, that would fill up all the oceans of the world? You add all the grains up and all the drops of water, and you've got as many protons as are in 1 cubic inch of copper. Another comparison, the size of an electron is to a speck of dust as a speck of dust is to the earth. The size of an electron is to a speck of dust as a speck of dust is to the earth. A final example, we're talking about now how small the universe is. The space between an electron and the nucleus, remember, is made up of the proton and the neutron. The distance between the electron, we're talking about an outer shell now, the space between an electron and the nucleus is 10,000 times as great as the size of the nucleus. In other words, the vast majority of an atom is nothing but empty space. The last one, The space between an electron and the nucleus is 10,000 times as great as the size of the nucleus. That is the same as placing a ping pong ball in the very center of the Houston Astrodome. It's the exact same comparison there. Put a ping pong ball in the very center of the Houston Astrodome, and you've got a comparison of the distance between the electron and the nucleus. In other words, the distance would be 10,000 times the length or the width or whatever of the ping pong ball. From the ping pong ball in the very center to the outside, let's say the very outside of the Houston Astrodome. Now we want to quickly talk about the potential energy that is in the universe. This is fantastic and amazing to realize the energy, the potential energy that's in the universe. First of all, protons and neutrons within an atom, which make up its nucleus, are held together with the density of 1 billion tons per cubic inch. Protons and neutrons are held together with the density of 1 billion tons per cubic inch. You see, this is where they got the idea of what we call the A-bomb, the atom bomb. Because there we're going back to physics and principles that relate to atoms. And they realize that if you've got this much density, 1 billion tons per cubic inch, we have being exhibited in holding the protons and the neutrons together in the nucleus, then what do you think could happen if we could split that thing in half? Think of the amount of energy that something like that would release. And so this is a principle that they used in making atomic bombs. This is what happened, of course, in World War II with the atomic bombs. Whenever they were able to split an atom, then you're going to have what you've got there in the production of the atom bomb is you've got a heavy isotope, and you've got it split in more or less 2 equal parts. And whenever you can split a heavy isotope, now an isotope is an element or an atom that's got more or fewer neutrons than it usually does. If it's a heavy isotope, then it's got more neutrons than what you would normally find in that particular element. So whenever you've got an atom bomb being exploded, what you've got is a cleavage or a division in that atom. It's got to be a heavy isotope, and whenever you can cut that thing in half, you have a tremendous amount of neutrons and energy released just from splitting that. Now, if you can keep those going and split one and split another and end up with a chain reaction, which is what you end up with in making an atom bomb, then you just got untold amounts of energy at your disposal. And this is exactly what the United States used in the summer of 1945 on Hiroshima and Nagasaki. Now, just the reverse of that is true with the sun. You've got nuclear fusion on one hand, you've got nuclear fission on the other hand. And just the opposite of that is true on the sun, whereas in an atom bomb, what you're trying to do is split the nucleus. You're trying to split a heavy isotope. In the sun, you've got just the reverse. You're trying to join 2 light isotopes to form 1 heavy isotope, such as 2, this is what happens in the sun, you've got 2 hydrogen isotopes that are light joined together to form 1 helium isotope. Whenever that happens, you also have release of neutrons and release of a tremendous amount of energy. And if you can keep it up in a chain reaction where one is splitting or one's joining and then the next one is splitting and the next one is joining, then you've got on one hand the release of energy and on the other hand you've got the release of these neutrons. And this is why they theorize that in so many million years the sun will burn out, because it's going to run out of hydrogen atoms to join together to form a helium atom that'll produce solar energy. And that's what you have just going on all the time. And on the very surface of the sun, you've got 10,000 degrees Fahrenheit on the surface. In order to maintain a heat like that, in order to heat our planet, you have to continually have these two hydrogen atoms joined together to form this helium atom. And pretty soon, according to them, if we're around long enough, we'd be running out of that. But anyway, getting back to this potential energy, protons and neutrons, I said, are held together with the density of 1 billion tons per cubic inch. It's pretty hard to get them apart. Secondly, this has been estimated by a German physicist that if we could fully utilize 1 drop of gasoline, it would take us around the earth in a car 400 times. You've got so much energy in 1 drop of gasoline that if you knew how to fully utilize it, get the protons and the neutrons to work just like you want them to do, you've got enough energy in 1 drop of gasoline to propel a car 400 times around the equator of the earth. Then thirdly, Einstein theorized that there was enough energy inherent in 1 drop of water that if you could fully utilize it, you could lift 200 million tons of steel a mile from the earth, just with a drop of water. You see, we'll never get to the place where we can fully utilize an atom like that. If we could, all you need is 1 drop of gasoline, and it would last for, you and your children and your grandchildren and their children, because who drives 400 times around the earth? I mean, that's a lot of miles to put on a car. That'd go around a long time, even for a taxi cab in New York. If you just keep passing what you had left from that 1 drop of gasoline along to the next car and put that in there, and he could go for 250,000 miles in his cab. And then take it out and put it in someone else's cab, and they can keep going too. Don't let people tell you that scientists are very bright or brilliant today. I mean, you got to fill the whole tank up, and it runs out before the week's over. And if they really knew what they were doing, they could, give us 1 drop. Now imagine how much that 1 drop would cost, though. It'd cost a life salary just to buy 1 drop of gasoline. Well, that's the energy that we have. You can see now why the Bible calls God the Almighty God, because He's the one that's put all this into play. Colossians 1:17, it's by Him that all these things consist. He's got to keep 1 billion tons per cubic inch of pressure to keep those protons and neutrons from floating apart. And He's got to do that for every atom. 1 billion tons. And that's why the Scriptures can refer to Him as the Almighty God. I want to close with a couple of mysteries about our universe. First of all, the time-light mystery, which says that as an object reaches the speed of light, and guess what happens? Time slows down. And I've got 3 examples by means of comparison to give you the time-light mystery. We're just barely scratching the surface on these things. We could just take years just studying these things. But that's not necessary. There are other more important things to study. The time-light mystery. As an object reaches the speed of light, it slows down. Several examples. These are points of destination that you're going to on a spaceship, and you're going the speed of light. And here's the comparison. Let's assume, first of all, that we're going to our nearest star, which is named Alpha Centauri, Centauri. That's our nearest star. If you were on a spaceship going the speed of light, you would get there in 3.5 years. While you were going on the spaceship, taking up 3.5 years, 10 years would pass here on the earth. If you were going, secondly, to the center of the Milky Way, in your spaceship, it would take you 21 years to get there. And while you were gone, you could look on your watch, and you'd watch 21 years go by. Keep a calendar and you'd count 21 years. While your 21 years went by in your spaceship, our planet would have gone through 50,000 years. Shows you time also is not infinite. Time is finite. How can you have the same, what we would call the same length of time? The spaceship, we're going to count how long it takes him to get from here to the center of our galaxy. We count 50,000 years. He counts the same way with his calendar, and he just counts 21 years. But we would say he was gone the same length of time, though. I mean, it either took till next week or it didn't. But next week to us would just be today to them. Thirdly, if you're going to our nearest galaxy, which is Andromeda, that's the galaxy nearest us, nearest the Milky Way, Andromeda, you would be gone 28 years in your little spaceship. While you were gone, we would go through 2 million years of history. You see, it multiplies very quickly, time here on Earth. While you were gone 28 years, we would go through 2 million years of history. One final mystery is the length, weight, time mystery. Length and weight and time. Here's the hypothetical assumption. You are boarding a spaceship that's 1,000 feet long, that weighs 1,000 tons. You are going to travel at 162,000 miles per second. Whenever you reach that speed, your 1,000-foot-long spaceship will now be 500 feet long. And your 1,000-ton spaceship would now weigh 2,000 tons. You divide the length in half, and you multiply the weight by 2. I can tell not everyone followed that one. You're going 162,000 miles per second. And you're in a spaceship. When you start off, you're 1,000 feet long. When you reach that speed, you'll only be 500 feet long then. But you also started off at 1,000 tons. Whenever you reach that speed, now you'll weigh 2,000 tons. You'll double in your weight. But you will cut your length in half, though. But you'd still have the whole spaceship. No, it doesn't cut in half and you lose the front of it. You still got the whole thing there. But now it's only 500 feet long. One other example. If a 30-year, that's why they're called mysteries, right? So don't ask any questions after this teaching. If a 30-year-old man could remove himself to another planet 30 light years away and turn a telescope back on this earth, he could watch himself be born. That's the truth. If a 30-year-old man removed himself to another planet 30 light years away and he got out of his spaceship in a hurry and he set up his telescope and he looked at Earth, he could watch himself be born. That's how fascinating just these two subjects of time and light are. You know, you think time, light, big deal. Yeah, they are a big deal, all right. They're much more than any of us could begin to even comprehend. What light and what time are all about. Time and light, remember friends, are only relative. Only thing that's big is God. Well, I'll let you think about that last one. But you know, it's interesting that at the same time, Matthew 10:29, God has his eye on the smallest thing. He said, not a sparrow falls to the ground without your Father. And then on the other hand, in 1 Kings 8, it says that not even the heaven of heavens can contain it. He's bigger than anything, but he also can keep his eye on the very smallest thing if he wants to, and he does. He keeps his eye on everything. You think about that last one. Just think about it a little bit harder. And I don't mean 10 minutes time. You got to think more than that, and you'll see how that's true. If you're 30 years old and you take yourself 30 light years away, you can turn around and watch yourself be born. Sure you can. That's a theoretical possibility. So before you, oh, that couldn't be true, you think about it, and then you prove to me how that couldn't be true. You just have to begin to travel the speed of light, and then we'd all understand things a little better. But time would just slow down then. And you'd weigh twice as much, but you'd be just half as long, though.
For a complete